Hey guys, Buildzoid here, and today we're going to be doing a demonstration of why Vdroop is good with Ryzen 7000. So the system specs here are the following: a 7950X that I purchased, the Gigabyte X670E Aorus Master, which was provided by Gigabyte, and a Kingston Fury memory kit based on single rank Hynix M die that I also purchased. So big thank you to the supporters for funding the purchase of the 7950X as well as the memory kit. Big thank you to Gigabyte for the motherboard. Now then, the setup that I'm running here, as you can see, it's currently running Linpack, and the CPU is at 5.125 gigahertz on the good CCD, and then 5.05 gigahertz on the bad CCD, right? Because it's a 7950X, there's a good CCD, there's a bad CCD. And this is a static overclock. For the core voltage settings, right now it's set to 1.15 volts with standard LLC, which is the highest Vdroop LLC that this motherboard has. Honestly, I wish there was an even droopier option, because looking at the oscilloscope, we can very clearly see that there's clearly visible undershoot, right? Like there's our average voltage, and we're getting like little downward spikes coming off of it. So there's like, this could probably benefit maybe from having even a bit more Vdroop than it currently does. Yeah, so that's not really the like. Gigabyte's arguably overly aggressive VRM tuning is not really the main focus of this video. So also, this is actually very common with AM5 boards. Like, AMD's spec for the stock load line is really, really aggressive, and due to how LLC settings are usually implemented as a ratio of the stock LLC, most boards actually don't have a like LLC setting that removes all of the undershoot. So yeah, but you do have the option to make the undershoot worse, right? So standard LLC is the highest Vdroop this board has, and also the lowest undershoot that this board has. Anyway, so it's been, running Linpack. It's not, like, it's been running Linpack. I have it set to run for 25 loops. We're not actually going to run it all the way to 25 loops. The main point here is to show that these settings right now are relatively stable, right? Like, this isn't instantly crashing Linpack. When Linpack is actually running, our core voltage is at around 1.08 volts, right? So there's like 70 millivolts of Vdroop. If I stop Linpack, you can see that the core voltage recovers up to like 1.14 something volts, right? Because even at idle, the CPU is pulling some amount of current, so there's a little bit of Vdroop on the core voltage, but we're approaching that 1.15 set voltage that I have in the BIOS. Anyway, at idle, we don't really have any undershoot because there's not a lot of current being pulled. And actually, when Linpack was running, so we're just going to restart it quickly. I'm just going to reset the statistics on the scope. Actually, I should have done that after Linpack starts. Just have to reset them again. Anyway, so yeah. When Linpack is actually running, we're seeing that, our average voltage, and the scope is hooked up to the back of the board, is around 1.156 volts, and our minimums are bottoming out at around 1.1 volts. So there's like 50-ish millivolts of undershoot, which is pretty, well, like, perfect would be like 20 to 30 millivolts of undershoot. So if, like, instead of this minimum being like 1.15 volts, if it was like 1.13, I would consider that a basically perfect result, because it's actually impossible for the minimum voltage to be exactly the same as the average voltage. That's not going to happen. But when we can clearly see downward spikes, that's like, okay, there's room for improvement there. There's a bit of room for improvement there. But anyway, so this is, reasonably stable, and our average voltage on the back of the socket is around 1.15 7 volts, and the load voltage, according to hardware info, is 1.08 volts, right? So now we're going to switch over to a very low Vdroop setup, and I'm not going to touch the CPU frequency or anything. We're just going to change the way the voltage is configured, and the stability is going to disappear, like, completely. In pre-testing, what I'm about to do instantly crashed. So hopefully, turning on the camera didn't invalidate my pre-testing. And I am going to give the ultra extreme LLC option a slight, benefit. I'm not gonna like. Well, okay, we're gonna start with 1.08 volts, right? Because that's the voltage that we were seeing in hardware info under load. So if we remove all the Vdroop, this should be stable, right? We're gonna go to ultra extreme. Our idle voltage is obviously a lot lower because there's no longer, like, the idle voltage isn't, 1.15 volts anymore. And you can already see that the waveform is just generally more spiky, which is not a good sign. We're going to pull up hardware info to sort of verify our voltages, because the SVI3 TFN sensor that's getting a voltage reading directly from the VRM's DyeSense circuitry. So that is a very, it's not a very fast sensor, but it is a very accurate sensor in terms of, like, the average voltage that measures is that's the voltage, like the average voltage that the silicon is seeing. And technically, you can hook up measuring equipment to that circuitry, but it's a massive pain to do. And you might potentially end up affecting the ability of the VRM to regulate the core voltage because that circuitry is rather sensitive. So anyway, here we are, hardware info, 1.08 volts at idle. We're going to fire up LinPack. In theory, the voltage should stay, well, we're going to see if we actually manage to read the voltage before the system crashes, but hopefully we manage to see something. I'm not sure if I used the right preset. 2, 5, 10. Yes, yes, no. .08. Did I forget to press start on LinPack? Looks like I did. Oh, yeah. I forgot to press start, so 1.08 volts. And hopefully okay, and you can see the voltage is still 1.08 volts, and it crashed. Right? It crashed so fast that we didn't really even have the opportunity to measure anything, but it was pretty clear that the downward spikes that we were seeing on the oscilloscope were far more severe than they were before. There was a lot more undershoot. So anyway, we're gonna give it a bit more voltage to hopefully delay the crash a little bit longer. I don't expect to see much of an improvement because there is a ton of undershoot in this configuration, right? Previously, we were seeing a difference from like 1.156-ish volts on the back of the socket down to like 1.1-ish. So about 50, 55 millivolts of undershoot relative to the average voltage on the back of the socket. Which actually on the back of the socket, we should be seeing less undershoot than what the silicon itself is seeing, because the undershoot is caused by the silicon going, for like the simplified way to think of this is the chip, like the core of the CPU goes low resistance. And so the voltage regulator, because the voltage regulator doesn't push current into the VRM, I mean into the CPU, right? The CPU basically acts as a very rapidly changing variable resistor, and the VRM has to do its best to maintain the core voltage at whatever, like in whatever voltage range we specify. And Vdroop is basically a way of making the VRM have to work less hard to maintain the voltage at the level that we were aiming for. Because the VRM can't respond instantly to changes in the resistance of the CPU, and it can't change. And the power plane also has like impedance. That means that even if the VRM did respond instantly, you still have the problem of the power plane's impedance getting in the way. Yeah, the thing is, so you get less, like, you have more undershoot at the silicon because the undershoot is caused by the CPU going low resistance, which means that the voltage at the CPU drops first, and then that propagates, like that voltage drop propagates out from the CPU to the rest of the power distribution network, in a way. So on the back of the socket, we actually see less undershoot than the silicon would be seeing. I'm not sure by how much, like how big the difference in undershoot at the silicon versus at the back of the socket is, because like I have in the past connected to the die sense circuitry of motherboards. It's not fun to do, and it causes all kinds of issues. So I prefer not doing that. Um, but yeah. So we're gonna try with now 1.09 volts, right? So more voltage than the stable settings needed, right? So 1.09 over there, and we're gonna see how much undershoot we're getting. There. So yeah, we're getting, oops. We're getting like 1.0, and the system crashed again. I stopped the oscilloscope, right? We're getting like 1.07 volts now instead of 1.1-ish. You can see that like you have the main sort of average part of the voltage over here, and then you have all of these massive downward spikes because the voltage regulator is really struggling to, well, maintain voltage regulation because there's no Vdroop. So, yeah. So there, that's why Vdroop is a thing. That's why Vdroop is good. And honestly, I would really like to see AM5 motherboards to offer more Vdroop in general. Because like the only AM5 motherboard I've tested where you had like the option to set the Vdroop so high that there wasn't any more undershoot, like unnecessarily high levels of Vdroop, was the Crosshair X670 Gene. That was the only motherboard where you had Vdroop options that were like excessive. Whereas like the ASRock boards that I've tested, the Gigabyte boards that I've tested, they all like, even on the highest Vdroop setting they have, you still have noticeable undershoot on the back of the CPU socket. So admittedly, you know, so there's probably, so I think there's probably room for like maybe a 30 millivolt improvement in terms of voltage regulation. At least on the boards that I've measured, if they just had a bit more Vdroop. Because yeah, on this board, even, you know, with the 1.15 volts and standard LLC, all right, and we're just going to run LinPack again. And I'm going to revert it back to the stable settings just to show that they do actually work. Like, okay, hardware info's up to 510, and I'm just going to scroll down before it manages to crash here. But yeah, so I do generally wish that like AM5 motherboards just offered higher Vdroop options from like. The funny thing is, even Asus low-end boards have the issue of like you can't set a high enough amount of Vdroop for static overclocking. Now, admittedly, this isn't a big problem because it really, like, if you're actually dailying a Ryzen 7000 series CPU, you really shouldn't be running it static as far as I'm concerned. There's very little like practical reason to do that for day-to-day usage. You're better off using the boost algorithm. But in certain like competitive overclocking scenarios, having an LLC setting where you have like what could be considered as perfect voltage regulation, as in no undershoot, can be slightly beneficial, right? Like I don't think there's like a huge improvement to be had from an even droopier LLC. Like I really don't think they would translate into any, like you might be able to shave off another 20 millivolts of average voltage. So maybe like 25 megahertz more core clock with the same voltage or something like that. But you know, it could be slightly better. And in theory, it should just be a matter of like adding extra settings to the BIOS for even more Vdroop. Because all of the AM5 motherboards use digital voltage regulators. So yeah. So 1.09 volts. horrible spiky mess on the oscilloscope, and crash. So now we're going to revert back to the high Vdroop configuration, which won't crash. And I really wish there was an even higher Vdroop option so that, you could run even less voltage or higher frequencies at the same voltage. That's kind of the point. And again, this does only affect static overclocking. For PBO, actually, this like overly aggressive stock load line from AMD actually works just fine. In fact, with the 7800X3D, I found that maxed like ultra extreme LLC seemed to help with stability when messing with like ECLK overclocking, which was very weird. Because for static overclocking, it does not work like that. But when you're using the boost algorithm, the CPU should actually have like a bunch of clock stretching functionality working. Which means that if the voltage is, if the voltage regulation isn't great, the CPU can actually just sort of temporarily slow itself down for when the voltage is outside of where it needs to be. And so that's probably why for like PBO style overclocking, this like really aggressive load line that AM5 normally has, it might actually just be beneficial. But for static overclocking, yeah, it's not ideal. Because in theory, if I had a little bit more Vdroop available, instead of, well, admittedly, the set voltage, like we might be setting like 1.2 volts instead of 1.15. But if there was a bit more Vdroop, the load voltage, instead of, because what we're going to be running right now is going to be like 1.08-ish volts under load. Instead of having to run like 1.08 under load, we might be able to run like 1.07 or 1.06. And yes, this is a very small difference. I do acknowledge that. But, if you're pushing for like benchmark scores for like rankings, 1% matters, or like a bit. So yeah, and you can immediately see the difference on the oscilloscope, right? Like there's just the downward spikes are just so much less, right? And a perfect LLC would be we wouldn't have downward spikes, right? Like we wouldn't be able to see any downward spikes whatsoever. But this sort of like small downward spikes situation, this is basically every AM5 board, with the exception of like the crosshair boards, because those actually offer like higher Vdroop settings than what AMD spec requires. Oh yeah, it's not going to crash now. Yeah, so that's our first loop done. So anyway, this is why Vdroop basically exists, is because your voltage regulator can never react instantly. And so by setting the sort of initial voltage a bit high, when the load changes, the core voltage doesn't like end up, going so low that you actually crash. So yeah, obviously the downside is your idle power consumption is a little bit higher. But your idle power consumption relative to your 100% load consumption is so low that I don't really, I don't care about that. And again, like this isn't something you'd be using for like day-to-day overclocking. For day-to-day, you really should just be using, well, honestly, I don't know that I would even bother with PBO, but if you want to do something, yeah, there's PBO. And that's going to give you better results in terms of just general day-to-day performance. So, yeah, this is really more for like maxing out benchmark scores. Like if you're trying to max out Cinebench and other like 100% core load, like 100% load benchmarks like that is where this is useful. For day-to-day overclocking, it's kind of irrelevant. So, yeah, anyway, This is basically a remake of a video that I did ages ago with like an 8700K. So now we have like an updated modern version. Everything that applied to the 8700K still applies to modern CPUs. Imagine my lack of surprise at that. Um, but yeah, that's it. Hopefully this was somewhat interesting. And thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, hoodies, posters, you know, the usual YouTuber merch. And I've also got a Bandcamp. There's a link to that down in the description below as well. And yeah, that's it for the video. So thank you for watching and goodbye.